Hi guys, sorry about that. I had some technical difficulties and had to reset some things. So we're going to pick up exactly where the last video left off. So that is on example 4.16. So let's go ahead and write out what B and C are asking for here. So for B, it says, what's the probability the text message user receives or sends two messages? Okay, and so for B, we want the probability that x is equal to 2. And then for C, it's asking what is the probability that text message users receive or send more than 2 messages per hour. So this is the probability that x is greater than 2. So these are the two probabilities we're working with. And if you remember, or if you saw the first video, part A, this is where we determined what our lambda was because we had to translate from days to hours. So in both of these, we're going to be using lambda equals 1.7292 as our mean. So let's switch on over to Excel and look at how to calculate B and C using Excel. So for B, we're doing the Poisson distribution. So Poisson, it has an equal to, so this is going to be non-cumulative, right? So we're given 2. Our mean that we found was 1.792. 1.79 or 1.7292. There we go. 1.7292. And because we're using the equal sign, it's going to be false here. So we get 0.2653. And then for the next one, where it wants to know the probability that x is greater than 2, because we're using greater than, we need the 1 minus. And then we're also doing the Poisson distribution here. This time, our x is still 2. And we have 1.7292. And this time we're using true because it is cumulative. So there's a 25% chance essentially that it will be greater than 2. So here, these probabilities we found. The probability that x is equal to 2. Was 0.2653, and the probability that x is greater than 2 was 0. I think I copied that down wrong. Hold on. No, we didn't. 0.2653. Good. And 0.25050. 250.050 essentially. All right, so let's move on to the next. So this is the last example we're going to do for Poisson distribution. So let's take a look. On May 13th, 2013, starting at 4:30 p.m., the probability of low seismic activity for the next 48 hours in Alaska was reported as about 1.02%. Use this information for the next 200 days to find the probability that there will be low seismic activity in 10 of the next 200 days. Use both the binomial and Poisson distribution to calculate the probabilities. Are they close? So, because binomial is success or failure, and Poisson is like a success or failure but over a period of time, you can estimate the Poisson distribution with the binomial distribution. So we're going to do this both ways to figure out the binomial distribution and the Poisson distribution. So in both cases, we want the probability that x is equal to 10. And so in the binomial distribution here, we're told that the probability, we're looking at x equal 10 out of 200, and the probability is this decimal form here. Okay, so for the binom problem, we're going to use the fact that x is 10 because we want to know 10 days. N is 200 days. The probability of a success is the percentage in its decimal form, so 0.0102. And so that's the information we need for the binomial. When we do the Poisson, though, we need to remember that Poisson is a little different than binomial because it's over a period of time. So we need to think about what the mean is that we're going to use. So our lambda in this case is going to be for 200 days, the probability is 0.0102. So for that entire time period, it occurs approximately 2.04 times. So when we use the Poisson distribution, our x is still going to be 10, but our lambda is going to be 2.04. So that's important to realize. So now we can go and find both using the two different methods in Excel. So let's take a look. So if we use the binomial distribution, we're using the information we just found. We're doing binomial distribution, where 10 is the number of days that it occurs, or our successes, out of total number of 200 days. And the mean, the probability is 0.0102 here. And we're going to use false because we're looking for exactly 10. And so we get 3.90169 to the negative power of 5. This E means negative power of 5. So this is scientific notation, right? So if you wanted to write this in standard notation instead of scientific notation, remember you're just moving your decimal 5 places to the left. Okay, so you're getting 0.00004 essentially, or let's put 39. So you can see how that works. And so if we moved our decimal back, it would be 39, 1, 2, 3, 4, 5. Very good. Okay, so for this one here, let's do the Poisson distribution. So Poisson distribution, this time we're still looking at, we're still looking at 10 as our success, but this time we had calculated our lambda over that 200-day period. And again, we're using equal, so it's going to be false when we ask about cumulative. And we get 4.472. So times 10 to the negative 5. So if we wrote this in standard form, it would be 0.45. So I would say that those are relatively close, right? They're both very small numbers, so they are relatively close. So chapter 5 is all theory. It just goes over the theory of continuous random variables. So we're keeping that idea of continuous now. So when we talked about binomial and Poisson distributions, we had either true or false on the end of our Excel statements because we were either doing cumulative or not doing cumulative. And that's because we could decide if it was cumulative or not because it was discrete, not continuous. Well, when we do continuous distributions, like the normal distribution we're going to see in a minute, it's always going to be true at the end of our statement because we are not going to have this breaking point, right, where we can decide. Okay, so let's take a look at continuous random variables and how they work. So this talks about the properties of continuous probability density functions. And so this is giving you the idea that's outlined here. I'd encourage you to read this. We're going to look at some examples and talk about these properties as we look at examples. So I'm not going to read this to you. So let's look at what this stuff actually means. So this is a continuous distribution here. It is called the uniform distribution because you can see if this was a histogram we were looking at, each bar, if you were considering from 2 to 3, 3 to 4, 4 to 5, those being bars, each bar would be about the same. So it'd be a uniform distribution. And so to find the area here of the shaded region, which would be the probability that 3 is less than x, which is less than 6, we would just take our length times our probability here. So your length is 3, and then you would multiply by the probability. So what's usually right here is a single probability that we can multiply by. So this is uniform distribution. We have exponential distribution, which is skewed, right? And we talked about the difference between skewed and uniform and all of those in previous sections. So you should be able to see that the exponential distribution is continuous, but it is skewed. So this is the normal distribution, which is the one we're going to focus on in chapter 6, and the one that we're actually going to do problems on. So it is our most commonly used continuous function. And we will also look at t-student distribution in the future, but for now, the only continuous function we're going to be focused on is normal distribution. So let's move on to the normal distribution. So this gives you the main idea of a normal distribution. A normal distribution is entirely defined by its mean and its standard deviation. It's a symmetric function, which means you can fold it in half at the mean. And so this is what a normal distribution looks like. It's bell-shaped. So let's talk about how to use normal distribution. So often we need to find a z-score. This is what takes any normal distribution and changes it to the standard normal distribution. The only difference between the normal distribution and the standard normal distribution is the normal distribution can have any mean and standard deviation. The standard normal distribution is that normal distribution that has a mean of 0 and a standard deviation of 1. That is the standard normal. And so when we want to change from a normal distribution to a standardized normal distribution, which is frequently, especially if we're comparing things that are not measured exactly the same, then we would use a z-score to be able to do that. This is the empirical rule that we talked about from chapter 2. It was using that idea of a normal distribution, particularly a standard normal distribution, and it gave you these estimates. Like if you were within 1 standard deviation, 68% of your values fall there. Well, those are estimates, but we can get more exact answers, or better estimates, I will say, using the normal distribution commands in Excel. So again, this is just showing you that we can have several different types of normal distributions, but a lot of times we want to change them to a standard normal distribution. One example of this would be, let's say the orange here is ACT scores, and the green is SAT scores. If we want to compare and set a standard for people entering our college with a certain ACT or SAT percentage correct, then we would need to change it to the standard normal distribution, because both of those have different scales that we're measuring on, right? ACT only goes up to like 32. SAT, a good score on that's like 1400. So it goes up more than that. So comparing 32 to 1400 would be difficult. And that's why standard normal distributions are so important. This also allows statisticians to create tables, and you will see some handwritten table work and how to solve these problems by hand using the table on the annotated notes. But we do use the Excel for the most part because it does all the background work for us. So we're going to go ahead and take a look at some examples. So the final exam score in a statistics class were normally distributed with a mean of 63 and a standard deviation of 5. Find the probability that the randomly selected student scores more than 65 on the exam. Find the probability that the random selected student scored less than 85 on the exam. So in part A, we're being asked that the probability of X being more than 65. And in part B, we're being asked for the probability that X is less than 85. So in this case, we would have to do this twice by hand, and it would make it, it would make it several steps. We would have to draw the graph, figure out what we're trying to do here, find the z-scores, find the probability, use the table, all of that. So to prevent that many steps, we can use Excel, which has that does all that background work for us. So let's take a look at the Excel. So if I wanted to do this, just like when we did Poisson and binomial distribution, it can only do less than or equal to. It can only do the less than portion on the Excel. So we have to use that same idea of whether we want greater than, less than, and so on. So let's jump back here and take a look at what the pictures would look like, so we have a clear idea. So here, our distribution would look like this, with a mean at 63, and we want to know greater than 65, so we want to know the probability that X falls in this area right here. Well, when we do it in Excel, Excel can only give you less than. So Excel can only tell you less than. So since this whole thing, the whole area under the curve is equal to 1, then we can do 1 minus anytime we're trying to look at a greater than. So when we do this in Excel, this is when we're going to use the 1 minus and then go in with the normal distribution and so on. Whereas when we do X is less than 85, our picture for that one, same mean, but it's less than 85, so we're looking at to the left, so we won't need that 1 minus when we do it. So we would just use the normal distribution command here. And you can look at the annotated notes for a better explanation, written explanation of that. But that's just a refresher of why we use 1 and 1 minus a distribution, and then why we just use the distribution. So for the A, we're going to do 1 minus because it's greater than. We can start typing normal distribution, and we're going to choose norm.dist. Our X in this case is 65. Our mean is 63. Our standard deviation is 5. And we're always using true when we do normal distribution. So we get that the probability is 0.3446. So for B, we're going to do normal distribution again. The X in this case is 85 because we're doing less than 85. My mean is still the same, and my standard deviation is the same. And again, we're always doing true. And we see that we get 1. So it is very likely it rounds to 1 when we do this, if we round to this many decimal places. So it's almost guaranteed that your score will be less than an 85. So let's take a look back at our example. So for this one here, which that makes sense, right? Because if I look at the picture I drew, 85 is really far into that tail, right? There's not going to be a lot of area left on the end of that tail because these kind of converge to a particular number. It gets closer and closer to 1, right? Because that area there is 1. All right. A personal computer is used for office work at home, research, communication, personal finance, education, entertainment, social networking, and a myriad of other things. Suppose that the average number of hours a household personal computer is used for an entertainment is 2 hours per day. Assume the time for entertainment are normally distributed, and the standard deviation for the time is half an hour. Find the probability that a household personal computer is used for entertainment between 1.8 and 2.75 hours. So in this case, we're doing a between function. So for part A, we want the probability that we're looking at 1.8, which is less than x, which is less than 2.75. So when we're talking about this, our picture we're drawing is got a mean of 2, and then we're looking from 1.8 to 2.75. And so we're looking here at this area shaded. So since Excel, again, can only do what's to the left, we can take what's to the left of our biggest number, which will give us all of that area, and subtract what's to the left of our smaller number, so that we get only what we want in between. So we're actually doing 2 normal distribution functions here and subtracting the smaller from the larger. So we're going to keep that in mind when we're writing our Excel command. So then for part B, find the maximum number of hours per day that the bottom quartile of households uses a personal computer for entertainment. Well, this time it doesn't give us an exact value, but it says bottom quartile. So when we're doing bottom quartile here, we're saying the bottom 25%. So what it's saying here is that this is 0.25. And instead of finding the probability, we want to find the x that would give us that probability of 0.25. So we want to find the x that gives us, I'm going to call it x1, 0.25. This will be a new function. This is called an inverse norm, where we're going from a known probability to a standard score versus going from a standard score to a probability. So we're going to look at both of those when we go to our Excel document. So for 6.4a, that we said is just using the normal distribution, and we're going to subtract using the greater and smaller values. So to start, I'm going to start with normal distribution. My larger x that I was looking at is 2.75. My mean that was given is 2, and the standard deviation that was given was 0.5. And again, we're always using true here. Then we're going to subtract the normal distribution that would be produced by that lower value. So our lower value was 1.8. Our mean is the same. Our standard deviation is the same. And again, we're still using true. And so we get that probability is 0.5886. Now for the other one, we're looking for an x value, but we know a probability. So we're going to use the norm inverse function. So that's norm.inv. We're going to give that probability, which is 0.25. We're going to give the mean, and we're going to give the standard deviation. And then it will tell us that occurs at 1.66. So if we go back here, what we're saying is this x right here is 1.66. And then this whole probability we found on the previous one was 0.5886. All right. So if we look at 6.5, in the United States, the age 13 to 55 plus of smartphone users approximately follow a normal distribution with approximate mean and standard deviation of 36.9 years and 13.9 years, respectively. Determine the probability that the random smartphone user in the age range 13 to 55 plus is between 23 and 64.7. Determine the probability that a randomly selected smartphone user is in the age range 13 to 55 plus is at most 50.8 years. So in these, A, we're doing a between again. Probability that 23 is less than or equal to x, which is less than or equal to 64.7. I've been using less than and less than or equal interchangeably here. That's because it's continuous. Less than and less than or equal to mean the same thing. Okay, and then because it's a continuous function. So then the probability here is that x is at most 58. So x is less than or equal to 50.8. So those are the functions we're going to do also. So let's run on over. So for this one here, we have the normal distribution. Again, this is between, so we're going to take the bigger information and then subtract the smaller. So we have 64.7 with a mean of 36.9 and a standard deviation of 13.9. And it's true, minus normal distribution of 23 was our smaller number, same mean, same standard deviation, and still true. Okay, and then so that is approximately 81.86%, or the probability is 8.8186. So for normal distribution here, this is strictly, or this is less than or equal to. So we're just going to use the plain normal distribution command with 50.8 as our top out value. Same mean, same standard deviation. And again, always true for normal distribution. So that's 0.8413. So this is our last example for chapters 4 through 6. So let's take a look. A citrus farmer who grows mandarin oranges finds that the diameter of the mandarin oranges harvested on his farm follow a normal distribution with a mean diameter of 5.85 centimeters and a standard deviation of 0.24 centimeters. Find the probability that a randomly selected mandarin orange from the farm has a diameter of larger than 6.0. So in this case, we're talking about P is x greater than 6. So if we did our picture here, we have 5.85 Then we have 6, and we're talking about greater than. So remember, we need to do 1 minus the normal distribution command. So that's what we're going to do here in Excel. We're going to do equals 1 minus normal distribution, where we're looking at 6, our mean is 5.85, and our standard deviation is 0.25, and always true. And so we get 0.2743 for the probability there. And so now, if you've gone along the entire lecture with me, you have filled in all of these, and you can see the numerical answers. And then when you go to the completed Excel, you can see the commands that are used for those answers. So these are the exact commands we used for those examples. All right. So that is all I have for you today. Have a great day, and I'll see you next time for Chapter 7.